Anybody try the hints, that like little program?
Oh yeah, I used it.
Did you?
Sometimes.
Okay.
Yeah, just to check my answer, like
Good.
to see if I was doing it right.
It kind of, it has a mind, you have to put like a space and then there's mine.
Yeah, and like it gives you like the steps, like how to do it.
Oh.
So like if you type in the equation, like the first box is like showing you like, okay, you need this many chlorines. And
Okay.
It's showing you like where they're being like transferred to.
Well, that's neat.
Yeah, and then it gives you the final balanced equation.
Well, very good.
I'm
Very good.
just to check my answer.
Great. So balanced equations. So this is a balanced equation between, this is when you guys burned your magnesium. You took oxygen from the room and it glowed and it ashed. So basically the stuff that was formed was magnesium oxide. But specifically, I think of it on a small level when I'm balancing it. Like, I think of two cute little atoms of magnesium and one O2 molecule go to form one formula unit, or excuse me, 2 formula units of magnesium oxide. Alternatively, we can kind of think on a larger scale. We can think the concept of a mole is the same number of particles. So if you had 2 moles of magnesium atoms, you could react them with 1 mole of O2 molecules to form 2 moles of MgO formula units. Okay? You guys are all sleepy today. All right. So, so when you balance an unbalanced equation, putting the right set of stoichiometric coefficients there, you are saying the relative amounts of reactants and products. So stoichiometric calculations make use of your stoichiometric coefficients. And I have a slide here of a brownie recipe. I should have brought brownies. I can't go wrong with bringing brownies. Ugh, I missed my opportunity. Although Friday it looks like I'm bringing in cupcakes. So, yeah. If you haven't taken that survey yet, still do it. But so stoichiometric calculations is very much like cooking. But the most basic, the obvious stoichiometric calculation is you have this mass over here. This is a reactant, and you want to know how much product you can form. So it's mass of reactant, mass of product. But it could be mass of reactant, mass of reactant, or it could be mass of product is what you know, and you want to know mass of reactant. So it's all about kind of relative masses. But we're actually going to start out with relative moles. So, yep, I missed my opportunity. Here's a recipe for making brownies. So we're just going to say that we want to make brownies, and notice that we're going to make 16 brownies with this recipe. Making me hungry just thinking about it. Let's say that you go to your cupboard and we want to make as many brownies as possible. And what if we have 16 eggs? Okay, you know where I'm going with this. And we have 4 cups of sugar. And we have 4 times all of this stuff. Okay, all I did was take, if we need 4 eggs for 16, what if we have 16 eggs? We can make 4 batches, right? Yeah. Okay. So here's how this works then. So we could ask, you guys told me I'm going to make 4 batches. Okay. What is, by the way, what's 4 times 16? It is. Thank you. Thank you. So make 64 brownies. Well, here, it looks like this. Do you buy this that, according to the recipe, we need 4 eggs for 16 brownies? 4 eggs will give me 16 brownies. Does that make sense? And the brownies are like the product, and the eggs are like the reactant. Awesome. Well, you know what we can do with equivalency statements. We can turn them into ratios. So here's how to get to our 64. So what if we had 16 eggs? I'm going to put it over 1. And I'm going to take this equivalency statement, because it came from the recipe. It came from a balanced equation, basically. It's the stoichiometry of the recipe. And I'm going to go ahead and take this and I'm going to put units of eggs on the bottom and units of brownies on top. Okay. So do you buy this, that it's going to be 4 eggs and 16 brownies? Okay. I was like, oh, that's not going to work, but it is. Okay, so units of eggs cancel. We're left with units of brownies. Now I'm going to go ahead and simplify this a little bit before I divide it out. And of course, I can divide by 4. So I divide this 4 actually goes away, and that changes that to a 4. Again, I'm glad I don't teach math. Are we all okay with that? Okay. So how many brownies can we make? It's that 64. Okay, 64 brownies. How did we get there? We got there from the recipe. And what do we start with? We started with the eggs we had in our cupboard. Okay, so that's it. All right. So that ratio, the whole 16 brownies over 4 eggs, right? That was kind of like a ratio from the recipe. We're going to make ratios out of our balanced equations. We're going to make ratios with our stoichiometric coefficients. Guess what? It's called a stoichiometric ratio. And how do we know which ratio to go with? Well, we look at our units. It's kind of like what we've been talking about all semester long. We look at our units. And we're going to start actually, it kind of not grams to grams, but convert from moles to moles. And I'll show you what I mean. So there are 3 things here. I almost said 6. Bless you. There are 3 things here. We have 2 reactants and 1 product. And we could come up with relative amounts of any pair. So for instance, we could focus on the 2 reactants, and actually that's what we're going to kind of focus on first. Our 2 reactants are our 2 ingredients. We could say, relatively speaking, we have, in this recipe, this balanced equation, we need 2 moles of magnesium for every 1 mole of oxygen. The inverse is also true. We need 1 mole of oxygen for every 2 moles of magnesium. We could instead focus on the magnesium and the product, and we get a 2 to 2 relationship there. Notice that these are the same, except they're the inverse of each other. Well, they're similar. They're the inverse of each other. And the last pair we could look at would be the oxygen and the magnesium, and they have this relationship. Sometimes students, when they're working their problems, they say, well, Mrs. Snipes, this actually boils down to a 1-to-1 relationship. Can I just go with 1-to-1? And I usually say, I would keep it 2 to 2 because you see where your 2's come from. You can't necessarily see where your 1's come from. Okay? But do you see where each of these numbers came from? That one came from here, etc. All right. So let's work a problem. Okay? And by the way, we're only going to get to that first assignment slide, but we're going to go beyond the first. We're going to get to the first assignment slide, not the second assignment slide, but we're going to go beyond the first assignment slide, so you see what I mean. So a lot of times what I'll do is I'll write under the species the information. So how many moles of oxygen? So I'll write question mark moles under my oxygen. Okay? I mean, why not? The the equation is there. Why not kind of make use of the equation with working your problem? So how many moles of oxygen are needed to react with, and then I'll put the other information, 0.245 moles of magnesium. So 0.245 moles. Okay? So I like that because it says exactly what the situation is. Okay? Now I'm going from a reactant, magnesium, moles of magnesium, to moles of oxygen. The next one we're going to work actually probably could be cleaned up. The question's not worded real well, but that's okay. So it says how many moles of magnesium oxide. Now magnesium oxide's the product, so I'll write question mark moles over here. So this is the second one. How many moles of magnesium oxide can be produced? It should have gone on to say from condition above. And by above, I mean number 1. So all this is saying is that we've got 0.245 moles of magnesium. Okay, so that's our second problem. Cool. Get a cup of coffee. No. So the first one, we're going from moles of magnesium to moles of oxygen. And of those 6 possible stoichiometric ratios, do you see where if we choose this one, that will get us there? Bless you. Because we're going to start out with moles of magnesium over 1. And if we go this one, then our units of moles of magnesium cancel. We're left with moles of oxygen, which is what we want to be left with. And one of the things with this calculation, and you'll get some practice at it tomorrow in lab, is you need to recognize this 2 came from there, and this 1 came from there. That's it. For the second one, we need a different ratio because we're going from moles of magnesium to moles of magnesium oxide. So we're going to pick this one. So our first term is just going to be that moles of magnesium over 1. If we go with this ratio, then moles of magnesium will cancel. We're left with units of moles of magnesium oxide, which is exactly where we want to be. But again, just recognize that this 2 came from here, and this 2 came from here. All right, so we work them. Here we go. First one. We start with the moles of magnesium over 1, 0.245 over 1. And then we said if we go with this ratio of the 6 ratios, 1 mole of oxygen is reacted for every 2 moles of magnesium you have there. Again, this 2 came from here, and this 1 came from here. All right, so half of 0.245. So that means that the moles of oxygen I'm going to need is 0.123 moles. So like we could go back to our whole brownie thing, and what did we say? We have 16 cups of, 16 eggs. And I don't have it in front of me, but I think it was 1 cup of sugar for every 4 eggs. 1 cup sugar for every 4 eggs. Okay, and then I could distill that down a little bit. Make that a 4, make that a 1. Okay, 4 cups of sugar, which you would have already told me if I'm quadrupling the recipe, but that's how that works. Okay, so then the last one, again, we start with that 0.245 moles of magnesium. Again, this problem isn't written really well, the second part of it. But now we want moles of magnesium to cancel, so we're going to put moles of magnesium on the bottom. We want to be left with moles of magnesium oxide, so we put units of moles of magnesium oxide on the top. And then what I do is I just usually go back and, once I get my units, I go back and revisit my balanced equation, and then I stick in my stoichiometric coefficients. I can do this math. Okay, so you get the same number, right? And it makes sense because the relative amounts of moles, and that's all when you balance those equations, all it did was relative moles. Didn't give you relative grams at all. We're going to talk about that in a minute. So the relative moles in this case was 2 to 2. So if whatever moles I start with, it can be the moles that I end with. It's magnesium oxide, so it makes sense too. Okay, so these will be due on Fabulous Friday. We'll take a look, and I will push these out under Twitter. If I ever say I'm going to put something on Twitter and I don't, let me know. I just forgot. Okay. So yeah, these should keep you busy enough instead of going to the next assignment. But So I kind of diagrammed in purple what we're after here. For the reaction below, calculate how many moles of NO2 are going to be formed. That's A through D, question mark moles of NO2. Then A through D kind of gives you different information. So for instance, A gives you the moles of N2O5. Actually, they all give you the moles of N2O5. So then in my hints, which you don't probably necessarily need, but it's just like we were talking about, okay, where we're going to put moles of N2O5 in the bottom because that's what we have, and we're going to put moles of NO2 in the top because that's what we're trying to get to. And we put the numbers here that I have a blue circle around. Those numbers in the blue circle came from the stoichiometric coefficients. Okay, so the coefficient for the NO2 is 4, the coefficient for the N2O5 is 2. So that's it. And then you'll do that for the other ones. And then for this one, and remember to get to my Twitter account, you don't have to have a Twitter account. Remember, you can just go. It's when I handed out my syllabus the other day, several weeks ago. The website. Just go there. So, and this one you have to balance it first. So don't forget that. And kind of writing information down underneath what you're trying to get to and what you know. Okay. Again, the blue. I don't like words, so I like numbers much better than words. So I took the information from the problem. And I said, we know that there's 9.3 moles of the lead, and we don't know the moles of the AgNO3 or silver nitrate. That's it. Okay. So then I kind of pretty much told you, except the purple circles I left them blank. Okay, but the purple circles here, this ratio that you're going to use to go from moles of lead to moles of silver nitrate, those numbers come from the balanced equation after you balance it. Okay, and then the last one. Again, several parts to this one. And I just did, you have to balance it first, that's A. And then they ask a couple of follow-up questions. For B, the question is, if you have 8.3 moles of aluminum, how many moles of H2SO4 will you also need? Again, those are two reactants, but bless you, that's totally fair game. And then my hint is just kind of what I did before. Again, I don't have the numbers to put there because you're going to have to balance it. Okay? That's all fun. Oh yeah, so you guys got this too. You have to show your work. I think we get desensitized to my blah, 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 blah. But make sure that you show your work and use factor label. Okay. I do want to go ahead and in tomorrow's lab, you're going to actually be doing stoichiometric calculations, but it won't be from moles to moles. It will actually be, and check this out, it won't be from moles to moles. It will actually be from grams to grams. So notice I kind of opened it up a little bit, and it's very symmetrical, so I'll kind of show you how this works. So let's say we have our same balanced equation, and now we know grams instead of moles, and we want grams instead of moles. So the information given is 0.30 grams of magnesium. And what mass of oxygen is needed? So question mark grams of oxygen. So I kind of alluded to it before, but when you read a chemistry problem and you think, if you don't get it the first time around, read it again, and it just kind of sinks in, okay? So here we go. So we actually did a moles to moles problem just a little bit ago, the 0.245 moles of magnesium, and we came up with half of that moles of oxygen, okay? And we used the stoichiometric ratio to do that. But you can't just quick and dirty go from our 0.30 grams of magnesium to a mass of oxygen using the stoichiometric ratio. because those ratios are relative moles, not relative masses. But we're okay. We can still do it. It just means we need to do something on the front end and something on the tail end. That something on the front end is actually something we've been talking about. You have to take that mass, that 0.30 grams of magnesium, and you have to convert it to moles. It's a molar mass problem. I always like the molar mass of magnesium. It's one of my favorite phrases. Okay? So how are we going to, well, I'll just remind you. We'll use the periodic table. Okay, we'll use the periodic table to go from the, and just straight off the periodic table, the decimal number for magnesium will do it for us. Then once we have moles of magnesium, then we can go to moles of oxygen using the stoichiometric ratio, just like we've been doing. So there was something on the front end, and then this is the middle part of something like you're going to do for your homework, moles to moles. And then there's something on the tail end because you're going to be left with moles of oxygen, and you want grams of oxygen. So it's another molar mass problem at the end. Okay? So we can get from moles of oxygen to grams of oxygen using oxygen's molar mass. Becky lost her pencil. Okay. So it looks something like this. So I'm going to go ahead and, do you guys already have these? I'm going to knock out the molar mass of everything. Molar mass of magnesium from the periodic table, 24.31. The molar mass of molecular O2, we have to take 2 times the decimal number of 16. So that's 32.00 grams per mole. And we don't need it for this calculation, but we will for the next one, kind of a follow-up. The molar mass of magnesium oxide is that 24.31 plus 16.00, or 40.31 grams per mole. So on your test, when you do stoichiometric calculations, you're going to have to keep up the good work of showing me the molar mass calculation up front. So now you could break this down, but into kind of parts, like get the moles, and sometimes students do, but I'm going to string them all together. You could get the moles of magnesium, then you could get to the moles of oxygen, and then you could get to the grams of oxygen. But I'm going to do it all in one term. So that first term is going to be the mass of magnesium, that 30.0 grams of magnesium over 1. So I need to use 24.31 somehow, but remember that's 24.31 grams per 1 mole. So I'm going to have to flip it, aren't I? So the next term is going to be 1 mole of magnesium over 24.31 grams magnesium. So this is an example where we have 2 things. We're dealing with magnesium and we're dealing with O2. So we have to be explicit with our which species we're dealing with. So now on the way to getting our answer, now I'm ready to go ahead and go from moles of magnesium to moles of oxygen. Stoichiometric ratio, exactly. So what I usually do, I'll just show you on this. For that middle part, I usually put my units of moles of magnesium down here, moles of O2 up there, and then, only then, and this is my stoichiometric ratio, only then do I go back and look at my balanced equation. Okay, so what number goes here in next to the magnesium? 2. It is 2. And then what number goes here next to my O2? 1. It is 1. Cool. Okay, so units-wise, we made the transition right there with that ratio is kind of how I think of it. We kind of made the switch from magnesium to oxygen. Now we have one more molar mass problem on the tail end. So we have moles of oxygen, we want grams of oxygen, and on that slide before we had 32.00 grams of oxygen per 1 mole of oxygen. So we're just going to use the unflipped version, aren't we? So it's going to look like this, 32.00 grams of oxygen over 1 mole of oxygen. And as far as I can tell, our question mark was grams of oxygen, so the units are great. We have arrived. So how many sig figs do we need to round that to? I'm agreeing with Colin back there. 2 because of this first mass. Yep. I brought calculators. Did anyone? Because you guys are going to want actually have another opportunity for extra credit in lab today, or in lab. In lecture. So you need a calculator. You guys want to borrow a calculator? You got your phones. You kids.
I didn't have my calculator in here.
Okay. So a lot of you are probably like me in this sort of problem. I kind of think of one big divisor, and I basically run along the top and I put my numbers, and then I run along on the bottom and put my numbers. And then I go ahead and in my calculator, I'll begin brackets. I'll put 0.3 times 32. I'll in brackets. I'll hit my divide by key. I'll begin brackets again. Put 24.31 times 2. I'll end brackets. And that gives me the right answer. All right. So is this what you guys got? 0.20. Every once in a while my slides are wrong, but this one that's pretty solid. Awesome. So kind of back to the brownies thing, okay? You know, if these were ingredients and you knew you had 0.30 grams of magnesium, you would need to use up 0.20 grams of oxygen. Okay, that's the stoichiometric amounts you'd need. So I have a follow-up question to that, and it looks like this. So follow-up question to that same reaction. All right. So what mass of magnesium oxide, so I find my magnesium oxide, I put question mark grams. What mass of magnesium oxide will be produced, that same mass we talked about before for magnesium, I'm going to put 0.30 grams of magnesium here. It goes on to say that with regard to the O2 has sufficient amount. Another way to think of that, I just now thought of it this morning, or just now. Another way to think of how much O2 we have actually must be what? Greater than 0.20 grams. Okay, they're just saying you have plenty. It's sufficient. What's sufficient? Well, 0.20 is what we needed. So actually I could put greater than, see I'm not a math teacher, greater than or equal to. Okay, but that's not the point. The point here is we're going to go from grams of mg to grams of MgO. Let's think of bingo, B-I-N-G-O, MgO. All right. So if I were to diagram this, kind of like we did before, it kind of looks like this. We're going to go from grams of Mg to moles of Mg, and how do we do that? How do we go from grams to moles? You guys know. What's MM? Molar mass, yep. And then we're going to go from moles of magnesium to moles of MgO. And how do we do that? Stoic, yep. Yep, stoic ratio. Perfect. And then we're going to go from moles of magnesium to moles of magnesium oxide, moles of MgO to grams of MgO. How we can do that? Molar mass again. They're very symmetrical. So here we go. The first term is going to be that mass of magnesium, 0.30 grams of Mg over 1. And we know we need to use 24.31. Remember, 24.31 grams per 1 mole. So we're going to have to flip it. So the next term is 1 mole Mg over 24.31 grams of Mg. Now this is where I would go ahead, and I know I need to use my stoichiometric ratio. I would draw my divisor. I would put units of moles of magnesium. That's what I have, and I want them to cancel. And I'm trying to go to moles of MgO, so I'll put that at the top. And tell me what numbers, what number goes in with the Mg?
2.
2, very good. What number goes with the MgO?
2.
Also 2. Perfect. So I do that, or you do that too. We're left with moles of magnesium oxide. We need to go to grams of magnesium oxide using magnesium oxide's molar mass. So that was that 40.31? Okay. Grams per 1 mole. So we're going to use the unflipped version, aren't we? 40.31 grams of Mg over 1 mole of Mg. Sorry, grams of MgO over 1 mole of MgO. So our units look wonderful. How many significant figures? 2. I'm liking it. So did you get this? Now, this is where, and I think I have a slide to kind of point this out, but do you buy this? We said we did 2 problems here, and they both dealt with 0.30 grams of magnesium. The first problem, we said that you would need to react 0.20 grams of oxygen with that amount of magnesium. This problem said that it's going to form 0.50 grams of magnesium oxide. You start to kind of see a pattern there, okay? The masses, yeah. Whatever you start with, you really should end with as far as the whole enchilada. All of your reactants should add up to equal the mass of all your products. Okay. Yep. Conservation of mass. Conservation of matter. Now, it won't, it should. If you're doing it theoretical, paper and pencil, it always should. In the lab, not so much. And we'll talk about that on Friday. Okay. So skip this one for now. What I want you to do is go to this slide. And again, this is for extra credit. Okay, we're basically going to do the first one together, and we're going to do a second problem on your own. This is balanced with coefficients of 1, 6, and 4. I think we looked at this on Monday. I'm not sure. So the first one we're going to do together, and then the second one you can work together. I mean, you can work in groups, but you need to write it down. Okay, and then once you're done with the second one, have me take a look and you're ready. You're free to go. All right, so let's do the first one. If I were going to write underneath what we're after, so what mass of P4, so I find my P4, I put question mark grams, is needed to react with, and I know my Cl2 is 1.25 grams. So it's very similar to kind of what we've been doing. Well, I'll go ahead and red just kind of show you the second one while I'm here. The second one, what y'all are going to do on your own, is what mass of PCl3, so I find my PCl3, so question mark grams of PCl3, can be formed from 1.25 grams of Cl2. Notice it says we have sufficient P4, so all our Cl2 will be used up. So that's the second one in red. So do you guys have these, all the cute little molar masses? Yeah. So to work those 2 problems, we're going to need the molar masses of both of the reactants and the product. So here we go. So what's the first term going to be here?
1.25 grams of Cl2.
Perfect. 1.25 grams of Cl2 over 1. I love it. And remember, kind of, this is where we need to use the molar mass of that thing. So what does that look like? And we want grams to cancel and be left with moles.
70.90 on the bottom.
Right. She's got it. 70.90 on the bottom. so 1 mole of Cl2 over 70.90 grams of Cl2. That's the molar mass. Perfect. Now we're ready for our stoichiometric ratio. And this is where I just put moles of Cl2, that's what I have, and so I'm going from, 2 moles of P4. Okay, so what number goes with the Cl2?
6.
It is a 6. Perfect. What number goes with the P4?
1.
It is 1. Everybody buy that? So the first step, actually, with the molar mass, that's 70.90 grams per mole for Cl2. Did you notice that when we did it, it was already done for you? That it had nothing to do with the stoichiometric coefficient. It had nothing. It only had to do with the formula, the species, the molecule. Okay.
I didn't know.
You didn't notice?
I wrote it down again, storage coefficient.
For this one, yeah, but not for the molar masses.
Oh.
Yeah. Okay, so now we're ready for the molar mass of P4, and what does that look like? What number goes on top?
1, 2, 3.8.
I can hear that.
I know.
123.88 grams of P4 over 1 mole of P4. Again, when we came up with that 123.88 grams per mole, again, it was already given to you, so, but it had nothing to do with the coefficient, nothing to do with one coefficient of 1. Okay, so how many sig figs?
3.
3. I'm liking it. Okay, so did you get this? 0.36. Cool. Now, I know you can get to the next number by adding, but you have to show your work. Because conservation of matter, you could just like add your Cl2 to this one, like your 1.25 grams to 0.364, and it seems like you should get the PCl3, and you're right. Okay, but I want you to go ahead and now work that second problem. And you can kind of, like I said, work together,